Optimization refers to the process of finding, in some sense, the best value for a given situation. For example, if we were talking about a company's revenue, then we would be looking for the maximum value. And on the other hand, if we were talking about something like costs, then we would be trying to find the minimum value. Now, with parabolas, that maximum or minimum value occurs at the vertex. Since we now have formulas for locating the vertex, we can use those formulas to quickly locate the optimal value of any situation that can be modeled with a quadratic equation. In this lecture, we're going to look at two theoretical results, and then in the next one, we'll see how they can be applied to some practical situations. So what I'm looking at here is a situation where the sum of the two variables is constant. So if the variables are x and y, that means that x plus y equals some constant c. And we're asked to maximize the product. So if we call that P, then P equals x times y. So I want you to keep your focus on this right-hand equation since it's the product that we're trying to optimize. So unfortunately, we can't work with this equation as it is because first, it has too many variables. And second, it isn't a quadratic equation, so it doesn't fit the models that we've been talking about in this chapter. Now, what we can do is take this first equation and solve it for y. If we do that, it becomes y equals c minus x. And now I can substitute that into the other equation, and a couple of good things happen. First, it goes from 2 variables down to 1. And second, if we distribute here, you can see that we do now have a quadratic equation. All right, so since the leading coefficient, remember I'm going to rewrite this, let's put the x squared term in front. Since the leading coefficient is negative, we know that the graph of the equation will open down, which means its vertex is a maximum, which is what we've been asked to find. Now, using our formula for the location of the vertex, we can see that it occurs when x equals negative c divided by 2 times negative 1. Remember, the formula is x equals negative b over 2a. B is equal to the c in our equation, and a is equal to negative 1. Now, if we simplify this, this becomes just c over 2. Okay, so that is the x value that will maximize the product. Now, what's the y value? Well, substitute again. Take c over 2, put it back into here, and we get y equals c minus c over 2, which is also c over 2. And now we have both values, right? If we know that the sum of two variables is constant, then the maximum value of their product occurs when x and y are both equal to half of that constant value. So this is kind of the obvious next question to ask. Right? What I've done here is I've reversed the roles. Now, instead of the sum being constant, it's the product that's constant. And what I'm trying to do is I'm trying to find the minimum value of the sum. And it will be a minimum, not a maximum. You can see this if you play with numbers for just a minute. Let's say x times y, that's our product, right? Let's say that equals 100. And I'm looking at the sum. I can drive that sum up as high as I want it to be, right? If you let y be 100, then x is 1, and the sum is 101. But if I let y be 1,000, x is not 0.01. X is just 0.1, and the sum is 1,001. There isn't going to be a maximum, right? But we can't talk about a minimum, all right? So how can we find that? Well, just looking ahead, this is actually not going to end up being a polynomial, all right? But it is something I want to discuss here because we can find the answer to this using the same kind of completing the square techniques that we've used to do previous solutions that did involve polynomials. Right, so let's go back here. Right, we're going to start from the same place we did before. We're going to say let x times y be a constant. I'm going to say let s equal x plus y. That's the sum. Right, so the product is constant, and it's that sum that I want to maximize. Oh, we're kind of in the same place now, right? We've got too many variables over there on the right-hand side. So what I'm going to do is I'm going to take this constraint equation, the xy equals c, and I'm going to solve this for x. Let's solve it for y, because you're used to seeing x's in the equation. So let's solve for y. Y equals c over x, and then I'll substitute that into here. Then s equals x plus c over x. Like I said, it's not a polynomial, right? It's not a polynomial. But look, work with me here for just a minute, right? Let's look at this expression. Let's look at the square root of x minus the square root of c over x squared. Right, now if you multiply that out, let me just do that over here. Square root of x minus the square root of c over x times the square root of x minus the square root of c over x. And when we multiply this, right? Square root of x times the square root of x is x. And we get minus the square root of c over x times the square root of x minus the square root of x, minus c square root of c over x times the square root of x. I'm getting tongue-tied. Plus these square roots multiplied, that's just c over x. Now look, over here with these square roots, I've got a square root of x in the numerator and the denominator in each one. They cancel. So what am I left with? I'm left with x minus 2 square root of c plus c over x. So this doesn't exactly get me back to where I started from, right? Because I have this extra term here, right? But if I add 2 times the square root of c, then this does equal the sum. Right now, I'm going to do the same thing. Right? This expression is a minimum when this part here is equal to 0. Right? Well, when does that equal 0? That equals 0. Well, let's solve the equation. Square root of x over this minus the square root of c over x equals 0. Let's move things around here. Square root of x equals, I'm going to move this to the other side, and then I'm going to split the fraction up. Let's make this the square root of c over the square root of x. Multiply both sides by the square root of x. The square root of x times the square root of x, awesome, that's just x. They cancel over here, and this equals the square root of c. That is our optimum value, right? The sum is minimized when x equals the square root of c. And all right, well, when x equals the square root of c, what's y? Well, let's come back up here to this y expression. Y equals c divided by the square root of c, which is just the square root of c. So there's my answer, right? The sum is minimized when x equals y equals the square root of c. You notice how there's some parallelism going on, right? When we knew that the sum was constant, then the maximum and minimum were at, then the maximum occurred when x and y were half the constant. But when we're talking about a product, instead of being half, it's a square root, right? So there's two kind of interesting theoretical results that we can get here. In the next lecture, we're going to kind of go the other way, and we're going to look at some practical situations and see how we can optimize those.